Yeah, we can hear you.
Thank you. All right, so let's do chapter 11. It's called Combined Heat and Power System. So that discussion that we had, that some of the cycle, when they reject Q rejected to the ambient, Q rejected is pretty high. Okay, like happen at very high temperature too. And so there it's useful. Okay, and so few years ago, maybe 5 or 6, the Department of Energy, they had this idea that all those steam power plants that we have in the country with like 40% or 60%, whatever, whether you have just steam cycle or combined cycle, where does that 40x% go? Or where is the 60% go if we are running 40% efficiency? It go into heating the atmosphere. And so they said, well, what if we, rather than heating the atmosphere, we heat something useful, like our dishwasher or our house in the winter? What if everyone has his own power plant in his garage? Then the Q rejected, rather than going into a big stack and going to the atmosphere, it really go into your heating your house. Okay? And so when you do this, I mean, maybe it's hard to imagine that you can do this for every house, but maybe for hospital, like San Francis or big hotel, DoubleTree, they have enough heating and electricity usage that they can actually do both of them on site. And when you do this on site, your Q heat rejected can be used. So in some countries where the power plant is like near downtown, you can send the Q rejected to the residential heating. You can send it around. Or in the university, for example, the power plant is on campus, they can use Q rejected to heat the place. But it's hard most of the time to do it, because the power plant usually is outside the country, outside the city, and the heating happen inside the city. So if you do it on site, that would be much better. The only problem is that when you do it on site, you usually deal with a small unit, and those small units don't have that high efficiency. Okay, so if I jump to the end of this chapter, you will see what I'm talking about. Those are the small units. Okay, so we call them micro combined heat and power units. What is combined heat and power units? You are generating electricity. There is a generator and make electricity, but also that heating go to the laundry room for a big hotel, or it go into the lobby for a big hospital that heat them. Okay, and they have different design. And you can see the ETA electric sucks 27. Why it sucks? Because it's a small unit. Small unit does not have the same efficiency like a really big power plant with a lot of feed water heater and a lot of regeneration and reheating. All those things that make the power plant so big to make the efficiency higher, you cannot duplicate on a small scale. Okay? But ETA overall, what's ETA overall? Well, when I consider my output, not just the electricity that I'm going to generate at 27%, but also that the Q rejected is not wasted. The Q rejected is actually heating my furnace or my lobby or my laundry room. Then the efficiency ideally can be how much? How much will the efficiency be if I think of them as both of them as output? What do you think? Theoretically speaking, it could be, say, don't be scared. If my output is not just work, but also the Q rejected, my efficiency could be 100%, theoretically speaking. It could be, theoretically speaking, 100%. Of course, I still need to send the exhaust with the fume to the outside. And when I send it to the outside, it has to leave a little bit hot, otherwise the water will condense. So I mean, it's not going to really be 100%, but That's what is beautiful about the combined heat and power cycle, is that not only the work net is your output, the QL is also your output. Okay? So that's why you see full load, like the heat overall is like 88. Huh? That can happen. Of course, emission is also a problem because a small unit like this will not have the control on the combustion process like a big power plant. Okay, so there are difficulty with emission, difficulty with the efficiency, difficulty with the cost, the price per kilowatt hour on those guys. There's something called economical of scales. If I'm making 1,000,000 unit, or if I make something really big, it's going to be cheaper than something very small. And if you guys have spent time reading about this big GE gas turbine, they will tell you why they are making them bigger and bigger, because of the economics of scale. And that's the same reason why the wind turbine that we see right now is big, and they will get bigger and bigger and bigger as whatever the material science people can do and make those plates lighter and stronger, the fluid mechanics people will make the turbine bigger and bigger and bigger. So the fluid mechanics people will build, or the aerodynamics people will build those turbines as big as the material science allow them to do. Okay. And so some of those units are really also using very exotic design, like you can burn wood on them or something, and you can generate electricity and heat. Or you not necessarily wood, but you can also just make it flexible so that you can burn different kind of fuel, not just natural gas. Okay. Very good. So this is what the few years ago the Department of Energy was saying, that the power efficiency kind of power generation efficiency as function of the unit size in kilowatt. Big steam power plants and big gas turbine as the one we have seen when it was like around what, 400 or 500 kilowatt. 500 no, it was megawatt. You hit 40, but all the small units that you buy, the small generator that you buy from Lowe's and Home Depot for emergency, you are running 25 and 30. Okay, and so in order to make that dream possible, that everyone has his own power plant at home, you need things that is of the order of 10 kilowatt. That is what a typical house would need, not more than 10 kilowatt. That house need to be here. So at that small size, you need to hit 40%. Then we will stop buying electricity from the grid, and we will make our own electricity using our own natural gas pipeline. Okay, as long as, of course, the emission is also clean. Otherwise, they will fine you for the emission that you are sending from your exhaust. I mean, there is, just like a few years ago, California had something called Rule 111 for the emission on any small furnace. Like before, it used to be small furnace in our attic or small furnace for your water heater it was exempt a little bit from the emission. And they said, no, any small furnace also need to be ultra NOx burner. And so that made a lot of the water heater company, like Carrier and Rheem and all those companies, they end up saying we need to switch to ultra NOx burners, and that makes them change their design from the fusion flame to premixed flame. What's the fusion flame? You send the fuel in air and it burns. Premixed flame is you send a mixture of fuel and air and they burn. And when you have a mixture of fuel and air, that gives you better control on the temperature and therefore better control of the emission, because the emission, especially NOx, depend on how hot the flame is. If the flame is really hot, nitrogen will react and will make NOx. But if the flame is cold, nitrogen will be like, I'm inert gas, I don't react. I'm gonna stay nitrogen. I'm not gonna react with oxygen. But that switch was really expensive because premixed flame need better control, and also they are noisy, they have need better acoustics. So it was like a whole deal in order to meet the NOx emission. So that's what we need. We need higher efficiency at small size and also better control of the emission. Okay, so what make this appealing? What make this appealing is that you can increase your efficiency, right? So he's saying how like combined cycle, they have efficiency that's really high as compared to like steam turbines by natural gas, which is like in this range. Okay, so this idea that why combined cycle is better, because you are using also the exhaust rather than sending the exhaust to the ambient, you are sending the exhaust to HRSG. What does that stand for? HRSG stand for heat recovery steam generator. Exactly. And so this idea, like that not only are making work in the turbine, the turbine generator, but you are also using the heat for something useful. Okay. And so that's something useful can be a steam cycle that generates electricity too. Right. So over here he's saying natural gas, you're burning. When you burn, there's efficiency lost in the burning because you don't burn every single thing. And so for our project, when we just think about just a gas burner for a swimming pool, don't assume it's 100% efficiency. Check the efficiency of those burners, of those water heater, gas-fired water heater. And you will see it's not 100%, but it's pretty high. Because, I mean, you're just making a flame, and as long as you spend enough time between the flame and the water will get the heat. But if the flame leaves very quickly or the hot exhaust leaves very quickly and you don't have enough coil, there's not enough pipe, you may end up losing the energy to the exhaust. Okay? But anyway, check on the efficiency of the furnace that you're going to choose. And then, where's the best cycle ever? He's doing 50% efficiency. It could be 65 or something, but he's saying you lose efficiency over here. Okay, and the rest basically go, you lose also electricity in the connection, in the network, in the lines. A funny story about this is, one time we were visiting Jinx Power Station, and he said, we were telling them, like, does it like really get lonely over there because you're all working all night? They work 24 hours, 7. And he said sometimes it's really funny, and he explained that one time we had a big storm, and the lines were cut in different parts of the city, and we had someone knocking at our door at the gate, and they had cameras and stuff to monitor the thing, and they said, yes, can we help you? And the guy said, we don't have electricity at our place, and I just kept following the line until I came to you. So he followed the electric line so that he can see what's going on. Anyway, so those lines lose also power over it, okay? So he's trying to say that the just generating electricity, you should expect something around 47%. He's trying to point out that, man, there is a lot of waste, and the waste happening in the thermal efficiency. It happened in the Q rejected, right? And so if we can use the Q rejected, that would be very appealing. And so there is an economical point to make this profitable, and that is the difference between the price of natural gas and the price of electricity. So if the natural gas is cheap and the electricity is expensive, like the electric company is charging you a lot for your natural gas, that make it even more appealing for a place like OSU or a big hotel to say, why wouldn't we generate our own electricity? So the difference between the price of the natural gas and the price of the electricity And it's not that easy to understand the difference between them because of the units, because they charge us with different units. Okay, that's not really convenient. So the electricity will charge you for kilowatt hour, like say 0.12 cent per kilowatt hour, but the natural gas will charge you either by BTU or million BTU. Okay, but if you can convert the kilowatt hour to BTU, then you will see the difference between the price of the natural gas and the price of the electricity. Of course, not every single city and state have the same rate, but $9 per million BTU of natural gas and $35 per 1 million BTU of electricity. So then if there is a big difference like this, of course, that's the profit of the electric company that's buying natural gas and turn it into electricity. And they have, you know, this big power plant that took years to build and engineers to run. And I mean, it understood. But we're trying to say that that's why a company like Apple, for example, you know, can generate their own electricity, because if the campus is so big, why wouldn't they generate their own electricity? Right? So the difference between those two guys, it has a weird name, and that name is spark spread. The spark spread is the difference between how much does the electricity cost compared to the natural gas on the same unit basis. And so a big spark spread and a need for electricity and heat in your campus, that is what would make you think we should do this. We should generate our own electricity, because electricity is expensive. We can make up our equipment very quickly. We will be able to generate back our money, and we can use both of them. Okay, and that's what you do for the rest of the chapter. And you can see how that spark spread is not just varying with season, but also vary for different places. So maybe in one place, he's picking different places all over the country. So maybe some places the natural gas is also very expensive. They don't have natural gas, for example. But if you look at your city and you figure out, wow, look at the big spark spread that we have, it's $140, for example, not just like 35, then that in a place like this, they will generate their own electricity. That makes sense to them. Right? So he's saying now with a CHP, with a combined heat and power system, your efficiency, after you turn the natural gas or the fuel, whatever fuel is, to energy, to BTU, say with 91%, then your conversion to electricity and heat could be up to 80. So theoretically speaking, up to 100%, or at least up to the 91% that you had in the boiler, in the furnace. You basically can utilize every single thing. That's what he's trying to say. Okay? And so, of course, also the demand for the electricity and the heat should be pretty much consistent. Otherwise, your unit will not run. Okay? You need to have a place. So that's why a hotel with a big active laundry room, or a hospital with a big active laundry room that always need the heat, that is a good place to have a system like this. But your household in the summer, maybe you guys don't wash the dishes that often, and you don't need to take shower that often in hot shower in the summer. But maybe with a big swimming pool that need to be heated all the time, maybe that is a good place to have a combined heat and power cycle for your own place. But the consistency is pretty important too, okay? So there is something called the usage factor. So kilowatt hour usage over the peak kilowatt over the day timed hour. So what he's trying to say here, he's trying to figure out, are we always running full load, equipment's running all the time, or we are spiky? So when you compare the kilowatt hour over the peak kilowatt, multiply by time, that will tell you how often you run your equipment. Okay? And by the way, big buildings here in Tulsa, their bill doesn't just come kilowatt hour. Their bill also come with peak kilowatt. So the BSO or whatever the electric company is, they monitor not just how much joule did you take from us, but they monitor when did you spike up, kilowatt. Like for example, if you have big air conditioning system, we call them chiller, right? So those chiller that cool the air for a big bank, or not big bank, but big like apartment complex. If that guy spike up even just 1 day per month, or like only at noon, during that they charge you for that. Because why? Although you didn't use it most of the year or most of the months, and your kilowatt hour is pretty low, because they have to have the right power plant size waiting for you, so that when you peak up, you can meet you. And we remember we got really cold the last months or something, remember? And they had to cut neighborhood on purpose because they just don't have enough capacity installed to be able to meet all that load. So that capacity waiting to run the load costs money. And who should pay it? The people who are using it. So that's why they charge for not just the kilowatt hour, but the peak kilowatt. They also charge, but very little for what? For completeness, you need to know this too. You know how the volt and the current, they are not in phase. For AC, for DC, the volt and current are basically don't have a direction, and the power is IV, right? But for AC, this is DC. For AC, the power is IV multiplied by cosine phi. What's phi? Is the angle between the volt and the current. So they rotate and there is a lag or a lead. The current would lag or lead depending on is the motor is inductance or capacitance. Is it like a coil or is it like a capacitor? And so worst case scenario, the I and the V would be like this. And the cosine theta would be, cosine phi, sorry, would be
0.
0. And if I calculate the power, it would be 0. So that if you're building running with something like this, you are not going to consume any kilowatt hour, amazingly. But the current is going back and forth in the wire, into the power plant, back to your building, into the power plant, back to your building. Okay? So the way you do this is that you have capacitance that will make the current pull it back. So
in this case, do we still have electricity in the house though?
but there are certain motor that can do this. Most of the cases we have a very the power factor is like 0.8 or something. So this is like for big factories when they can actually have something like this. So this is called in big power in a big building they will charge you for the kV the kVR, the reactive power kilowatt. Sorry, we call it kilowatt kWR, reactive power. So the reactive power is the component that is basically not real, the imaginary part. So the IV cosine phi is the real part, and this part is the imaginary part. Okay, so the kVAR. So those are the three things that they will charge you for. Okay, the kilowatt hour that you are actually using, that's the real power you are using, and the peak kilowatt and the reactive power. Okay. Anyway, the point is the peak kilowatt, if it's always there, that make your load look something like this, and that make you can run your own power plant. But if you are spiking so much, maybe it's waste of money to buy a big power plant just because you run 1 day. What is the point? right? You better do it from the grid then. But if you always have the same power, more or less, then you can generate your own electricity. So we need big spark spread so that we make our money back. We need a load and a heat. Like we need both of them so that we can benefit from running our own plant. And we need to be a little bit consistent so that we can run our equipment efficiently all the time. Usage factor should be close to 1. If we are very small on this, that means that we're going to buy our equipment and we're going to sit next to it and it will run very little. Okay. So he's calculating the cost of the natural gas, the cost of kilowatt hour, and after that he calculate the spark spread. Okay. So he's just like, this example is just for you to learn how to calculate the spark spread. So what does it take to do this? Same unit. You need to make $1 per BTU. What is the problem? The problem is you would have different units for both of them. They will tell you the natural gas per cubic feet, for example, and they will tell you the electricity per kilowatt hour. So you need to turn the cubic feet into BTU and you need to turn the kilowatt hour to BTU. So that at the end of the day, you have everything per BTU. Make sense? Very good. So the typical number, ETA boiler, 85%. What's that? That's how much is lost in burning the fuel. Okay, the central power plant or thermal efficiency, 35% because it's a small unit. The central chiller, that is like the heating that's done by heat pump. Its COP is 2.5, that's typical. Okay, electricity is done by a gas turbine, 30%, and recovered thermal energy, how much you can actually get from the gas turbine to run a heating process. You can get 35% of it. And this is cooling, COP, a chiller, with COP 0.7. So notice how the COP of a heat pump is different from the COP of a chiller or refrigerator. Why? I mean, they are running on the same cycle. This is pH diagram. And the cycle would be this. But while the COP of a heat pump is Q dot H over W, and that's always 1 or more. It has to be 1 or more for a heat pump. The the COP of a refrigeration or a chiller is Q dot L over WC. And this is not guaranteed to be 1. Why? Because, I mean, if the temperature is like really low, and you are taking it from here all the way to here, you can see how the Q dot L, see, it's very small compared to the work. So the COP of a refrigeration cycle is not going to be always bigger than 1. I mean, you are lucky if it's actually 1. But the heat pump, the QH, is always bigger. Why Q dot H is always bigger than work? What's my proof for that? I'm saying Q dot H is always bigger than work compressor. Why? Who can prove that for me? Free homework problem. Why Q dot H is always bigger than work compressor, and that's why COP of a heat pump is going to be always bigger than 1. Question is, why Q dot H is always bigger than work compressor? And the COP, which is Q dot H, over work is going to be always bigger than 1. Why? Because Q dot H is work plus Q dot L. So this guy is always bigger than 1. Of course, then QH is going to be always work bigger than W. I mean, you take the Q dot L, you add the work, and they all leave at QH. Okay? So using a heat pump for heating is no brainer because it always have a COP greater than 1. It's going to be always better than an electric heater, which has a COP or an efficiency of 1. Electric heater, COP or efficiency is just 1. Burn electricity, make heat. But with a heat pump, you get a little bit Q dot L. Okay? So why we don't all have electric, a heat pump, electric water heater, a heat pump, and electric? Why we all don't have a heat pump water heater? Because the equipment, you need this in your closet. You need a condenser, evaporator, and a compressor between them to run your water heating, right? So it's really cost, not efficiency. Efficiency, they will work, but it's the cost, right? I mean, when you think about it, some people also even just have a water tank, like a tank water heater. I mean, those are horrible efficiency-wise. Why? Because you keep them hot all the time. I mean, that is a loss of energy. I mean, that water sitting there, no matter how good the insulation is of the water tank, it's still dissipating heat. But why people buy them? Our second place we lived in was a townhouse that we rented, and it had a tanked water heater. And it's because it was really cheap, right? A better version is a tankless water heater because it heats the water on demand. When you open the water goes through the pipe, the heater figure, oh, water is coming, let's turn on the flame. And he burned the flame and the water get hot. Of course, you're sitting next to the shower, still cold, still cold, still cold, 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 and your child is screaming, no, it's still cold. And then after you wasted a little bit of money for like maybe 2 minutes, then you can step in. If it was a tank water heater, the water is ready for you all the time, right? But on the expense of what? It's always losing the joules to the ambient, right? So cost is a big deal too. Okay. So you guys can read those examples yourself, but what's really important here is this part. Yes, 11.5. This is important. So when it comes to the efficiency of a combined heat and power cycle, the efficiency now is 2 parts: power and heat. Those are the outputs. Okay, the power and the heat is the output, and the fuel that we're burning in the burner is the input. Okay, so this is the thermal efficiency of combined heat and power cycle, and theoretically speaking, it can go to 100%. So 1 year, the problem in the final was just like this: calculate those things, and a lot of students didn't even know what I'm talking about. Okay, so eta thermal is power, so that's the megawatt generated from the generator, right, connected to the turbine, and Q is the heat that you are utilizing, and F is what you are burning in the burner. The cycle, however, sometimes look a little bit different than this. So from what I said right now, you guys are probably thinking that a combined heat and power cycle is always Here is the boiler where he's dumping the fuel. Here is the work, or in this chapter, he's just calling it the power output, right? And then you would think that the Q, or the heat, is what he's dumping in the condenser, what is lower at the cycle. So on the TS diagram, so no, not pH. On a TS diagram, that cycle would be like this. And so you would say Q rejected is basically this part, what he's dumping in the condenser, right? But sometimes this temperature is too low. It's like he's condensing at 40 degrees C or something. And he does not want to heat at 40 degrees C. Maybe he really want high temperature to do the laundry or something. He want to like boil the hell out of those clothes because it's the hospital. And you really need hot water. So what they will do is they will extract the steam when it's a little bit hotter, and they will have something like this. They will have a heat exchanger over here when they can get their Q. Okay, so what I'm trying to say is that the combined heat and power cycle doesn't have to be always extracting heat at the bottom. It could extract heat in the middle of the cycle. Okay, of course, that heat in the middle is more valuable than the heat at the bottom, because the heat of the bottom, that's totally waste for us. We just have to reject it. But the heat of the bottom, I'm sorry, in the middle, when we extract from here, which is where? It's like this place. Like he's extracting heat over here. This is bad for us as a cycle because it's cutting from our what? From our work. I mean, you are losing steam that was supposed to go to the turbine, right? But you are getting better heating. So we now just realize that not all Q are created equal. Some Q are better than some Q, and that is based on their GBE. No, they are based on their temperature. If your temperature is, you give me 100 joule at 100 degrees C, is very, very valuable than 100 joule, same 100 joule at 40 degrees. Because 100 joule at 100 degrees C, I can do more useful stuff with it. Not only I can do more quality heating, certain processes need really high temperature, but this 100 joule at 100 degrees C, I can make work out of it. I can take this 100 joule at 100 degrees C and put a cycle under it and get work. But the 100 joule at 40 degrees C, that is garbage. This is just throw it in the ambient. There is no more availability, right? Because it's already very close to the ambient. But anyway, that make us realize that, or make him realize that the work and the heat are not the same. One of them is way better than the other one, okay? And so that's why they say, well, when you calculate the efficiency, you shouldn't really add them, They are not the same. So there is something that is another formula for it. So the FERC is calculation is, I forgot what the FERC stands for. Here, yes. The Federal Energy Regulatory Commission. So the Federal Energy Regulatory Commission calculate the combined cycle efficiency by this power plus Q over 2 over F. So they just think, well, the Q will have an efficiency of 50%. Of course, that's a function of when are you extracting the Q. If that Q at very high temperature, yeah, maybe you can get 50% efficiency out of it. But if you take it at really low Q, a low temperature, you are not going to get 50% efficiency, right? But anyway, they had to stick to a number. And so their number is this. So P plus Q over 2 over F. That is their efficiency of combined cycle. So in that exam, I just wanted the students to know what are the different definitions. So I said calculate the thermal efficiency of combined cycle and calculate the FERC efficiency, the Federal Energy Regulatory Commission efficiency. Okay, make sense? Fuel utilization efficiency. Okay, what is fuel utilization efficiency? How much did we benefit from our fuel? So the fuel, if we just going to generate power out of it, his efficiency would be the power over efficiency. I got this many kilowatt hour or this much BTU in work, and I burn this much BTU. And so the thermal efficiency or utilization efficiency of that fuel is, output over input. Okay. So now when you are generating also Q in it, that's really great, right? Because your fuel is now utilized more. By how much more? Rather than saying it's P plus Q over F, you would actually take it here. So it's P divided by F minus the Q. Okay? Minus the Q. Why? Because that heat that you used in the process heating could have been done with a fuel. So you are actually using less fuel now. Okay? But the fact that you generated or use, say, 1,000 BTU in that process heating or heating the laundry room or heating the lobby with 1,000 BTU, your fuel is actually more than this. The saving in the fuel is more than 1,000 BTU. Why? Because there's efficiency in burning the fuel. Like in burning the fuel in the boiler, there's also efficiency for it. Atomization and complete combustion. And so it's like actually Q over eta Q, whereas eta Q is thermal efficiency of producing the energy from the boiler. Make sense? So that is another definition for efficiency in combined cycle. From the fuel point of view, how much did we really benefit from that fuel? It's the power that you generate divided by F minus Q over eta boiler. Okay? And the last one is the fractional energy saving. Okay, what's the fractional energy saving? 1 minus F over P over eta P plus Q over eta Q. Okay, so when you think about it, this is how much did we save because of the combined cycle. So those 4 definitions just require you to, if this happened to be a homework or an exam problem, it's just basically filling in the numbers in the formula. So you just need to know where is the formula and you fill the number. And they are all of them are just a way to make you appreciate that when you use some of the heat, especially if it's waste heat, that take your efficiency from thermal efficiency that's typically 40 to 60% to theoretically speaking 90 or even 100%. Okay? That's it. Okay? And so you can see this example exactly do this. You take the numbers, put it in the formulas, all those formulas, and calculate them. All right? All right, we finished, and we talked about actual system that actually exists, how people are using it. We actually have a whole research in Oklahoma State and Stillwater about biofuels. So because there is a lot of grass, they had a few years ago, they had big grant for turning switchgrass into fuel. And they also work on like how they can gasify the biofuel. So if you have grass or wood or whatever, all those things, biomass, how you can make it into a gas, because then the gas is easier to run things with. You can run gas turbine with it. You can move it easily rather than just having a bunch of grass in you. So a lot of people work on that area too. Very good. Questions? Got it?
I think the last lecture you said isothermal compression was like the best compression. You didn't give a free homework problem for it, but
No one answered me.
I'm kind of curious as to what.
So remember we said last time how isentropic compression you would think it is the best, but actually isothermal is the best. And that's why people always use, or like whenever, not always, but whenever it's possible, they always use, or they prefer to use intercooler in the compressor, right? Because they want the heating that happened in the first stage to lose. They want to cool it so that when you start the second stage, you start from cold again. So it's really, really great to stay as cold as possible while you are compressing. And so this company, I think it's called Ultra X. Another isothermal compression method. I forgot the name. Ultra X. Isothermal compression, energy storage. So what they did was they said we don't want the air to get cooled. Okay, so how can I always make it prevent from heating? What's the best thing that will suck heat out of my air? Big surface will work, but that's expensive and it has to be slow. But what have really big heat capacity that can suck the heat out of my air as he's getting hot? Yes, water. So if we spray water while we are compressing, the water will cool him, and that heat in the water can be utilized later on. I get cold water, hot water that I can recover the heat out of it. But my compression happened at very low temperature. Okay, and so they had a patent, and they actually built, yes, Sustain X. So it was really funny because over the, like, I taught this course for a bunch of years, and so every year I will tell the students, well, here is, they come up with the patent. The next year was they actually raised $100 million to build their plant, and then the year after that, well, here is the plant, Sustain X of Bloomberg. They must have a site, smart grid. I think if we actually look at picture, maybe we'll see their plant. Where's my image? Oh, Sustain X station, power plant, or energy storage plant. How big an emergency? Let's see it also. I can see more. Ah, it's okay. But that's just a cartoon, huh? I think 1.5 megawatt isothermal compression. So, but I guess this is a good point to actually tell you how I was one time sitting next to a guy that has a lot of patent on his belt. He was actually a graduate of OSU. He was one serving in our industrial board. So like we have an industrial board out of, like, once you graduate and you become very famous and rich, we will bring you back so that you can help us to design our courses. for the next generation. And so we were sitting with one of those guys, and I was telling him, like, what is the secret for like having a lot of patent and invention like this? And he said, it's very easy, actually. All you need is to really understand the problem. If you really understand the problem, the solution will become very easy. So the problem, if the difficulty is not to come up with a solution, he's saying the difficulty is to really understand the problem. Okay, so what was the problem? Why the air is getting so hot? How can we? So you need to understand, why does he get hot, and how can we prevent him from being hot? His temperature is getting hot. Can we suck the heat out of him? And then the idea will hit you. Okay, very good. Does this answer the question? Yes. Okay, so next is chapter 14.